Welcome to Saitechinfo channel, my dear students. In this session, let us discuss the temperature dependence of rate constant. It means how the rate constant, that is speed of the reaction, varies with respect to temperature. So we should be aware of some key terms, that is the parameters like rate constant, activation energy, that is the energy of activation, Arrhenius frequency factor, temperature, then gas constant. So these are the very important parameters that is associated with this concept, temperature dependence of rate constant. So it is given by this equation K is equal to AE power minus EA divided by RT, where K rate constant, A Arrhenius factor or frequency factor, and then energy of activation, that is EA, or gas constant, T temperature, that is in Kelvin. So first of all, let us discuss about the activation energy. You just look at this graph where there is a reaction coordinate in x-axis and potential energy is given in y-axis. Let us consider hydrogen and iodine. So these two gaseous molecules, they react together to form 2 moles of hydrogen iodide. So these molecules, they collide each other, and we cannot expect all these molecules first of all to collide, and all these collisions will be fruitful, and all these collisions will be responsible for the reaction to take place. So it depends on so many factors. At the time of collision, in fact, when we talk about collision, there will be head-on collision, there will be grazing collision, there will be a sidewise collision, etc. So, you know very well the head-on collision will be very active. And by this collision, what happens here? That is, the energy is getting activated, that is, excited. So, the energy required to form intermediate complex, it is the activated complex. So H and I, they combine and they get excited. So they go to the highest level of energy. But it has to take a call. So after the collision, there should be some reaction, is it not? So now it comes down. The energy, whatever the energy released, acquired, or required, now it should be released. So during the release, probably it may attain the same status, then we call it equilibrium. When it goes down, so lower the energy, higher will be the stability. So that indicates the progress of the reaction. Therefore, the energy is released when the activated complex decomposes into, that is, formation of a new product, Hi. So the potential energy is getting increased at the activated complex stage. Okay, right. Now, as I already discussed, the all molecules do not have same kinetic energy. So it would be very difficult to predict the behavior of one molecule because it's something like a batch process. So it would be very difficult to identify a single element and analyze and predict its behavior. But batch-wise we can do. How? That is, Boltzmann and Maxwell, they applied statistics. That is, that they applied statistics and introduced the probability factors also to predict the behavior of what? Large number of molecules. Underline that point, large number of molecules. So based on that, we can say, for instance, see that is in the lower energy, kinetic energy, there will be, let us consider x-axis, kinetic energy as x-axis, and the fraction of molecules. What do you mean by fraction of molecule? Here it is Ne divided by Nt. Ne means that is number of molecules with energy E, whereas Nt, that is the total number of molecules. Okay, so we can represent this by, that is Ne and Nt. There is a ratio. So, as I already mentioned, all the molecules are not going to be excited, or all the molecules are not going to acquire the energy. So, they will be acquiring the energy at different stages, is it not? Different ratios. So, in fact, that is, there will be some portion, well, let us say that is this much portion of molecules will be having the highest energy. Do you understand? And that is called the most probable kinetic energy. So, what happens when we increase the temperature? There will be a shift of this portion towards right to the maximum kinetic energy. And not only that, there will be, that is, the curve will be further widened. Okay, so the width of the curve will be increasing. So you just look at this here, you can see initially, that is, there was a, see, are you able to get the two curves here? So this is at temperature T. But when we increase by 10 degrees centigrade, what happens here? Now, probably the energy of activation may come down. That is, this activated energy, the highest peak may come down, but it widens and it is distributing itself to the higher energy kinetic, higher kinetic energy portion. So it tries to occupy, I mean, it tries to involve more number of what? The molecules. So the higher will be the fraction. So peak, what is peak here? The most probable kinetic energy, that is represented by the peak here. That is this one. And the less fraction at low. So there will be less fraction at low and higher kinetic energy. So in the lower kinetic energy as well as in the higher kinetic energy, there will be less portion only. Less means that is the ratio will be here less. Then the higher fraction will be in the most, I mean, probable kinetic energy or the high excited energy. So with the increase of temperature, now we have increased by 10 degrees Celsius. What happens here? The curve is broadening. Do you understand? So there is a broadening of curve and that leads to the maximum point moves. So this is the maximum, is it not? This is the maximum. You have the maximum here. This is the maximum and this maximum is shifted towards the right. Are you able to follow? So, and not only that, the area under the curve, that is constant because the total probability is 1. Normally that is when you say probability of one fraction plus probability of another fraction is always equal to 1, is it not? The net probability is 1. So, so the area of the curve is a constant here, but the increase of temperature increases the fraction of molecule. It means it widens. So there is more participation, is it not? So the rise in temperature by 10 degrees centigrade almost doubles the rate constant. So this is a very important aspect. So that was discussed by Boltzmann and Maxwell. Then it is called the most probable kinetic energy, this one, and this most probable kinetic energy is shifted towards the right, that is towards the higher kinetic energy side, and there will be more active participation of the molecules also. The more fraction will be there and the area of the curve remains constant, but the curve is widened, broadened, okay, right, and that is why this portion can be called the energy of activation, okay, and this area, this shaded area, this black portion, that is, this is energy of activation. This shaded area is the fraction of additional molecule which react at T plus 10 degrees centigrade. So now let us again introduce this. K is equal to A into e power minus EA divided by RT. Let us introduce a natural logarithm on both sides. So natural log K is equal to natural log of AE power minus EA divided by RT. So we know according to product rule, log of xy is equal to log x plus log y. And we know very well when we that is introduce logarithm in the exponential term, these two terms are cancelled. That is being the inverse. Okay, inverse functions. Log and exponent are inverse functions. So they are getting cancelled and we are able to get minus EA by RT. So minus EA by RT and plus, since it is minus, plus of minus, minus, then log. So we have split according to the product rule. Okay, right. Now we have to convert this natural log to the base 10, for which you had to multiply by 2.303. So multiplying by 2.303, you can convert it. So 2.303 divided into log k is equal to 2.303 log to the base 10a, then minus EA by RT. So you can write as such. Now what you can do, you can multiply the entire equation by 2.303 for our convenience. So log k is equal to log a minus EA divided by 2.303 RT. So at two different temperatures, we are discussing about two different temperatures. So in that case, there will be two rate constant because with the increase of temperature, there is an increase of rate constant. So log K1 is equal to log A minus EA divided by 2.303 or T1. Log K2 is equal to similarly log A. So it is not going to be changed, being constant. So minus EA divided by 2.303 or into T2. Now let us subtract, that is 1 from 2, equation 1 from 2. So 2 minus 1. So log K2 minus log K1 and the log A term is cancelled. Now you have minus EA 0.2.303 or can be taken outside being the GCD. Now you have 1 by T2 minus 1 by T1. Now log K2 by K1 is nothing but that is minus EA of 2 by 303 or into, then take the LCM T1 T2, so T1 minus T2. Now this minus term can be eliminated by interchanging T1 and T2, is it not? Therefore, log K2 by K1 is equal to EA divided by 2.303 into R and then into T2 minus T1, that is nothing but delta T divided by T1 T2, where K is the rate constant and for first order it is per second. Then EA activation energy in joule per mole and you have got the gas constant 314 joule per Kelvin per mole. That is the universal gas constant and the temperature should be indicated in, it should be expressed in Kelvin. Okay. Now let us discuss a problem based on this.